Welcome to the class of high performance computing for scientists and engineers, and we are in the last module of this course, which is GPU computing. In last few lectures we looked in detail on CUDA programming, and we have seen CUDA programming can give good performance which scales very well in GPUs for matrix vector products, matrix products, matrix solvers type of scientific computing applications. Well, now I want to show you another paradigm of GPU programming, which is OpenACC based programming. Why is this important? Due to the fact that we are talking about scientific computing when looking into HPC. Scientific computing is mostly done by people who are working from long in domain sciences like physics, mechanical engineering, chemical engineering, biology, chemistry, materials, etc. And they have, as expected, usually limited exposure to computer science. When we look into GPU computing, we understood that there are several issues for which one need to take care of the flow of instruction and flow of data from CPU to GPU and within the GPU itself. The optimizations in GPU using CUDA requires substantial expertise in that particular field. So somebody, when directly coming from a non-computer science background, is a programmer on its own for the particular applications on which he is working, can find it difficult to work in CUDA and write CUDA parallel programs. This is one very serious issue, and therefore we will see in a while that multiple industries working on accelerated computing came together, multiple organizations, industrial organizations came together and thought of doing something for the people in scientific computing. There are few important aspects for which I thought that introducing OpenACC or an easier way of developing accelerated programs can be important here. One is that, as I understand, many of us have limited expertise in terms of computer science or software based applications. We mainly look into our domain specific applications, so it will be easy for us to use something like OpenACC, which require less involvement in terms of data and instruction handling. The next might be that many of our CS friends will actually look into the applications developed and maintained and utilized by people of non-CS background and see that they are using some languages or some a paradigm like this, OpenACC, through which they are parallelizing their program. The third issue might be that many times you are not the developer of the program, but you get a program and you have to use it. If you can get hold of a GPU code, you might like to parallelize it with your limited expertise. So you can find OpenACC useful, or you are working with a group who are using OpenACC or this type of parallelization, because as I am mentioning every time that many times people are challenged with their programming knowledge, especially GPU. We understand GPU require certain expertise, that expertise is missing in that group. So there can be many instances for which this is important. As a matter of fact, I collaborate with a group from NVIDIA in Bangalore, India, and their system analysts and engineers suggested me that a module of OpenACC will be very vital in this course, because they are seeing many scientific application community is migrating towards OpenACC program. Well, with this background, we will see what is OpenACC. It's a directive based parallelization. So shall see what is directive based parallelization, but you can think that it is very similar to OpenMP type of programming, where only we are using the directives in that program. We are not calling any functions or not using any libraries, only using the directives. How can we do data management in OpenACC? Because we understand that in GPU, calling data from CPU RAM to GPU RAM, copying data and copying it back is important. So what do we do for that? How can we parallelize a loop using OpenACC? Because most of the scientific computing applications depend on iterative loops. How can we parallelize it? And we will see some of the examples. Mr. Bharat Kumar Sharma, as I mentioned him, he is a senior solutions architect from NVIDIA, and many of the slides I will show have a direct contribution from his end, and he is one of the key person who suggested that OpenACC must be a part of this discussion. So, if you look into OpenACC forum, what they try to assert is more science, less programming. A person working in a science engineering domain will be more focused towards science, less focused towards programming, and that is what community expects from him. So, you should spend less effort in writing the program or developing the program and thinking how can I bring certain data from device memory, what should be my compute global memory access ratio, how should it be mapped to the shared memory, how it can be accessed by different threads, what should be my optimum block size. These things we expect a scientist to less worry about these things, so that he can do better science. I mean, this is inevitable. For getting better science, for getting accurate solution, he has to learn large problems, and going into GPUs might be inevitable. But while doing that, he must be less bothered about parallelization efforts. Rather, he should think more about should be able to spend more time about science and use more of the developed tools in his domain. Well, so we know GPUs can give very high scalability. We have seen 90 times scalability in some of the matrix computing example in last class. However, thread management and data handling demand serious programming effort. With very less background, like in OpenMP, with a very initial background, one can jump and start converting his program. But in a CUDA program, if you have your legacy code, it is very difficult to directly convert it into a GPU code. You have to identify the portions which can be parallelized, you have to do the right thread algebra, many things are there. You have to copy data from GPU to CPU, etc., allocate variables, many operations are to be done. So, CPU based codes are not very easily ported into GPUs. Like MPI and OpenMP, you can start with the basic C code and then start modifying it. Very soon you can develop a parallel code. But in a CUDA GPU code, the CPU based codes cannot be very easily ported into GPUs. Using CUDA or OpenCL, you may have to rewrite the code, and some of the legacy codes we can think about, they are of millions in line size. So, rewriting the entire code might be very difficult. OpenACC or Open Accelerator, and also another thing is that performance depends on optimizing several factors like block size, memory access, shared memory, many issues are there. So, if people from different industrial organization working on GPU and accelerator based HPC thought of proposing something like OpenACC or Open Accelerator, where the compiler will take care of these parallelization efforts. Programmer has to only identify that which part of his program he wants to parallelize, and the compiler itself will take care of that. So, this is developed by a programming standard developed by Cray, CAPS, NVIDIA, PGI, and the standard is designed to simplify the parallel programming in heterogeneous CPU GPU systems. This is a directive based parallel programming model designed for performance and portability. So, with less effort you can get optimized performance, that is one aspect, and portable means you can take it from across different platforms. You can run on a multi-core system, you will get good performance. You run on a NVIDIA GPU, you will get good performance. You go to a Intel multi-core system, you will get good performance. You go to an AMD GPU get good performance. All this has been taken care of, that compiler will see which hardware it is working on and get look for that performance. NVIDIA is supported in both CPU, multi-core CPU and GPU architecture. So, I missed it here, there will be multi-core CPU and GPU architecture and can launch parallel port of the computational code in either of them. And overall it can take accelerated computing easy for domain experts. The caveat is that this is for shared memory systems, this is for single instruction multiple data type of model parallelization. For distributed memory system you have to use you have to use MPI. OpenACC cannot be used that, but it can replace some of the functionalities of OpenMP because it works on shared memory system. So, let us recap OpenMP program, because we talk about directive based parallelization, and if we can recall that directives we have used in OpenMP program. So, if we see that in particular location we want to use we want to parallelize that, use this shared and private memory, and then some of the work will be done in a critical manner, that each thread will do on its own, there will be a sequentiality among them. So, this is that this region will be parallelized, this region will be critical. This is called by OpenMP directives, right. These statements hash pragma or exclamation OMP for Fortran or hash pragma for C are the OpenMP directives. In OpenACC, similar directives are used for parallelization in multi-core CPUs and or accelerator cores or GPU cores. So, let us look into directive based parallelization in little more detail. If you have an application which has to be parallelized, that the program application means the program which has to be parallelized, then there are three general methods for that. One is calling parallel library. Say you have a particular scientific computing example where there is a matrix solver, you call a hyper library which has inbuilt parallel matrix solver function. So, you call that function. You can use compiler directives like OpenMP, we have seen OpenACC is also there, or you can use programming languages. This can say you are using OpenCL, that is a programming language for parallelization. It gives you very good performance, it is very flexible. However, you need to learn the language, you need to learn the syntax and semantics. In library it is easy to use, you usually get good performance also, but there are certain it is not much flexible, there are certain restrictions on that. But in between that you can use compiler directives which are easy to use, and you can have your own code. In library you have to use their library function which has been built by somebody else, but you can use your own code and parallelize it using the compiler directives. Compiler will read the directive and do the part of parallelization. So, you only have to direct compiler that consider this part and parallelize it accordingly. So, if we look into an OpenACC program, we can see different directives like hash pragma, ACC, data, copy in, copy out. This is a directive for data movement, how data will go from CPU to GPU and GPU to CPU, etc. Hash pragma ACC parallel, compiler knows that this zone will be parallelized. Then hash pragma ACC loop, gang loop, vector, these are different instructions of different way of parallelization of the iteration loops. So, these are the directives which you call inside the put inside your older CPU code and get a parallelized code. OpenACC.org presents this set of directives. This is a non-profit organization in which many companies are there, and they help scientists to do more science and less programming for HPC. And this platform is developed by Cray, CAPS, NVIDIA, PGI, and the OpenACC which we are talking about, this particular directive based parallelization works on number of platforms including NVIDIA and AMD GPUs and Intel multi-cores, Intel accelerators, etc. So, the efforts, if we see in parallelizing an OpenACC job, we call this, there are incremental efforts. So, is it incremental effort? You have your older serial code, then you have to put only the OpenACC directives, and then you can add annotations to expose that they are parallelized. Only introducing these directives will parallelize the code. So you take your older CPU code, look into the parts which you can parallelize and start putting the directive. After putting directive at one particular region, you see that you are getting right results. You can run into a single processor, it will run like this older code. If you run it multiprocessor, it will run, or GPU, it will run as an accelerated code, but the results must be same. Check the results. Once you check that this part is correct, you understand that this part has been parallelized, go to the next part. So because in this type of programs there are thread fork models, fork join models of the threads. Each fork you look into and parallelize that. Begin with a working sequential code, parallelize it with OpenACC, and then verify and annotate that part and go to the next block, parallelize it. And so that is why we call that's an incremental way of parallelizing. Look into each part, parallelize it. Well, then it is portable. You develop a code using OpenACC, and that code will run in all of these platforms. So once you develop a OpenMP code, it will run in all of these platforms, and in each platform compiler, say we go to a multi-core CPU platform like a x86 CPU, or we go to an AMD GPU, they are different platforms, but compiler will identify that what is the hardware, what is the architecture, and how data should move, how the kernel should be launched, what should be done for the right parallelization. So this will be left on the compiler. It itself will do that part of that optimization. And if you run on a single processor, the sequential code will be maintained. It will give you the sequential result. So that's why it's a portable. It's a portable program also. If the code is run on a single processor system, the sequential performance remains the same. The compiler can ignore OpenACC code additions so that the same code can be used for sequential and parallel execution. So when you run on a sequential platform, or when you run on a platform where some of the parallel drivers in terms of hardware or software are missing, compiler simply ignores the pragma line and runs it as your old sequential code. So you do not need to maintain multiple codes for different platforms. And it has a low learning curve. Low learning curves means you say you have identified a parallel zone, you written hash pragma SEC kernels. This directive tells the compiler that this has to be parallelized. How will it be parallelized? You do not need to know about that. It's a starting point. You can do some certain things to improve the performance, but to start with, you do not need to know about that. Compiler will take care of that. So it is easy to use and learn. You only need to know few directives. You have to identify that this location can be parallelized. You have to have some basic idea of parallel computing and call these directives, and compiler gets the hint and works that. You do not need to your knowledge in C, C++, Fortran is sufficient. You do not need to know low level details of the hardwares as well as how to manage those things. You do not need to know the details which you know for CUDA programming. You do not need to go for that. So one of the issue might be that you may not get the best performance because you are leaving everything on the compiler, and compiler has has been optimized for certain general applications. For your specific applications you may not get the best performance. So for that you may have to do some other optimization, or in some point of time you may not get the best performance using OpenACC. If we compare, in many cases we can see CUDA can give you better performance, or OpenCL can give you better performance, because you have more flexibility in terms of from programmer's point of perspective there. But you can get reasonably good performance with less effort. In some time you can do things, if you are not very efficient in CUDA programming, you can do things in a wrong manner. But in OpenACC, as compiler is taking care of everything, it will give you reasonably good performance. So OpenACC syntax is in C, it is hash pragma SEC, then directive with the clauses, and then it is followed by the structured code block many cases. In Fortran it is hash $colon $, exclamation $, SEC, directive and clause, and then this is paired with a matching directive surrounding a structure block, and in many cases you show that the directive has been ended by $SSC, and inside this whatever you put will follow the directive. Directives are commands in OpenACC for altering our code. Clauses are specified inside the directive or additions to the directive. We will see some of the clause later. A pragma in C++ gives instruction to the compiler how to compile the code. Compilers that do not understand a particular pragma can freely ignore it. It will not give you a error or a bug. If compiler is unsure about a pragma, it will ignore it, and the remaining part, if you take away this pragma or if you take away these two lines, the remaining part is your sequential program. This will operate in that manner. So they are very optimized to give you error free outputs, but that can hinder the performance. If compiler is ignoring, the application engineer may not understand that compiler is ignoring that part, but for CUDA or even for OpenMP, if it is ignoring, you will get an error message there. A directive in Fortran is specially formatted comment. Likewise, so it's a specially formatted comment starts with exclamation. So if it is if compiler doesn't understand it, it's an explanation, it will be ignored by the simple Fortran compiler. ACC informs the compiler, both case ACC is present, that it's an OpenACC directive. Similarly, you know, OpenMP you have seen OMP is present there. OpenACC provides compiler options for porting the code from multi-core CPUs and GPUs, and this is very important. That why this is a PGI compiler instance is shown, and PGI is one of the developer groups of OpenACC. So when you run this, you put the compiler option -TA is equal to Tesla managed. It shows that when this will be compiled for Tesla is a GPU, NVIDIA Tesla GPU card compiled for a GPU card with managed or uniform memory access data. If you write compiler option -TA multicore, the compiler will know that it is compiling it for multi-core CPUs. So just by giving compiler option, it can be the same code can be compiled for different jobs. In unified managed memory access model, because we are using Tesla managed, separate CPU to GPU copy or vice versa practice is not practiced. So data is not copied separately from CPU to GPU or GPU to CPU. Rather, we consider a unified memory access, that the entire data is present in somewhere combining CPUs and GPUs, and whichever device will require that, host or device who will require the data will migrate towards that. You remember at the beginning of discussions on GPU, we talked about unified memory access. So by using Tesla managed, we can use unified memory access. So this is an unified, in a general CPU GPU access, there is a CPU RAM, there is a GPU RAM, and data is copied in between them. In a managed memory or unified memory access, there is a single combined memory, and data is migrated towards CPU and GPU based on the application. So that also you can do by providing the compiler access, that it will consider a GPU and consider as a unified memory access GPU. So the memory management is same as SIMD multi-core programs, and you develop a program for multi-core OpenMP type program using OpenACC for multi-core system using SIMD model. The same program just with changing OpenACC program, not an OpenMP program. For OpenMP you can also use GPU, but some other features are included. But if you develop a OpenACC program, multi-core program, the same program can run. If you write -TA multi-core with the compiler option, it will be built for running in multi-core system. If you write -TA Tesla managed, it will run in GPUs. If you want to run this in a non-unified memory system like this, the memory systems we considered in our previous CUDA examples, CPU has a different memory, GPU has a different memory, and data will be copied from CPU to GPU or GPU to CPU as required. Just use the compiler command -T is equal to Tesla. Tesla managed will give you a unified memory access, simple Tesla will give you a non-unified memory access. In CUDA also you can use unified memory access in the recent versions of CUDA. We have not discussed that, but you can use that. You can look into CUDA C programming guide and find that. Well, in OpenACC, unified memory accesses are important, because then the same code you don't need to copy from device to host or host to device. It's like a unified memory or managed memory case, and the same code can go to both multi-cores and GPUs. In multi-core system, especially in unified memory access or UMA multi-core systems which we talk about, we do not need to, there is a single RAM which all the cores are accessing. So if you are using managed or unified memory, it's working in the similar manner. Without managed memory, the code required to be rewritten for data management similar to CUDA, that is CPU to GPU copying. And this CPU to GPU copying is obtained by data clauses, data directive, that you write PragmaACC data with the clause that CPU to GPU or GPU to CPU, how the copying will be done. Using this directive, you can copy the data. We will see some of the examples soon. The data directive defines the lifetime for data on device beyond individual loops. During the region, the data is essentially owned. When we give in the data directive, within this region, any data we talk about is owned by the accelerator. It is on the GPU, we talk about that. But we have to copy from, if you are using unmanaged system, then you have to copy from CPU to GPU, and within the directive it will be in the GPU. And then we can copy back to from GPU to CPU. Data clauses, the clauses express the direction of movement and shape and size of the data. These are the clauses. Copy tells that memory is allocated on GPU, and data will be copied from CPU to GPU and GPU to CPU as required. When copying from CPU to GPU will be done, then it will be CPU to GPU during entering the parallel part. After the parallel part, it will be copied from GPU to CPU. So both CUDA mem copy host to device, device to host is taken care of. Copy in says it will be copied from CPU to the GPU. It will do CUDA malloc, allocate the memory, as well as it will do the copying. Copy out will do GPU to CPU copy all along with allocation. Create will just do the allocation part. Then sometimes we use an update command, which is like a synchronization command. If there are multiple iteration loops, the data which is lying on the CPU and on the GPU, it is required that they are synchronized. So use update, that it considers one of the data. Self means CPU and device means GPU. Consider one of the data, so CPU data, and checks that it agrees with the GPU data. So whatever part is not copied, it copies it there. And they have their utility for some of the examples. For synchronization, you need update. For you need to use an input from CPU, you need copy in, so on. We can observe they have similarity with CUDA mem copy and CUDA malloc. The data clause in OpenACC is PragmaACC data copy in, and copy A of size A has size n into m and nu has size n into m. That means A will be copied to accelerator when needed and copied back from the accelerator when the part is done, and nu will be only copied from the CPU to the GPU. GPU is the accelerator. Now this copying is defined only for the parallel region, but we might require the data even outside the parallel region. Maybe again the another parallel region will be done and the similar variable will be operated, but if we say that was available only for the previous parallel region, again we have to copy the data. Copying from CPU to GPU is a costly affair. So we can set that when this will be copied to the GPU, and then we can say that it is flushed off, it is deleted from the GPU. These terms we also can set using directives. And data regions are always not very structured, and some data may be required to remain in the device even after the parallel region is over. Enter and exit clause with the data command. Data directive can help us. Enter clause will tell that data will go in the GPU and stay there. Exit will say that now this data is not required, GPU will erase the data. So this is like PragmaACC enter data copy in. So A, B are copied into GPU and they will stay in the GPU, and C is created in the GPU, C will also stay in the GPU as long as we require it, and then we write C is equal to A plus B. After that we delete AB, so AB is deallocated from the GPU. GPU does not store any part of A and B, and C is copied from CPU to GPU, but yeah, so C is the entire part is exists the data is removed, erased from the GPU memory, ABC all erased from the GPU memory. But if we run another loop here, we run another parallel loop here, run a few more parallel loop, run a sequential loop, etc. here, the A, B and C will still remain in the GPU, that GPU copy will be unaltered. This eliminates excessive movement of data from device to host and vice versa, and therefore increases performance. OpenACC parallelization directive, and we have seen earlier the simplest parallelization directive is kernel. If we can identify a particular region which has to be parallelized and write the pragma ACC kernel, this construct will identify this region, that take that region of the code and check if it thinks that it may contain parallelism. This parallelization is done by the programmer, the construct directive is given by the programmer, but it's left on the compiler to parallelize it. Compiler will check that whether there is sufficient data independence and iterations are there, it consider it for the parallelization, and then if it checks that there are sufficient data independence, then it will automatically parallelize it. So compiler will analyze the region, identify which loops are safe to parallelize, and then accelerate those loops. Developers will do little or no developers with little or no parallel programming example, or who are working on functions that contain many loops which you cannot go in individual loops and parallelize it, can find this kernel directives a good starting place for OpenACC acceleration. So this is developers with pragma OpenACC kernels, and there are many parallel loops. It will try to see that which of the loops can be parallelized here. Programmers need not find data independence and parallelization scopes. Compiler will do it for on the target device or accelerator. So you just write pragma ACC kernel, it will take care of the rest. Parallel loop is similar to the OpenMP equivalent. Instead of kernel, you can use parallel. Parallel gives you more flexibility and more liability, as more responsibility as a programmer, that you have to identify that this is a parallelizable loop, and you have to tell how the program will parallelize it. Parallel loop is an assertion by the programmer that this is safe and we desire it to be parallelized, and then compiler will parallelize it. In kernel, compiler will programmer may not know that if it can be parallelized. Programmer thinks that it's a compute heavy zone, ask the compiler to parallelize it. In case of parallel, programmer has to be sure that this has to be parallelized, and also programmer has certain flexibility in terms of how that can be parallelized. When encountering the parallel directive, the compiler will do something. Because we think of parallelizing in accelerators and GPUs, compiler has something in mind. It will try to, in a parallel regime, it is known to the compiler that this is for sure to be parallelized. It will try to do some equivalent of the blocks, threads, etc. So what it will do, it will launch in the parallel regime, it will launch many gangs. Each of the gangs will do exactly same work. But now if there is an iteration and we ask this to be a parallel for loop, then each gang will take part of the iterations and operate over the number of iterations. So it is something like what each block is doing, and each block is operating number of threads. Similarly, the gangs will execute that. There will parallel regime. If there is a parallel regime, that will be executed by all the gangs. If there is a parallel for regime, then each gang will take part of the iterations and do it. Say we have a OpenACC parallel, pragma ACC parallel, and then pragma ACC loop. That means this for loop has to be parallelized. Then each gang will take some iterations of the loop and run them in parallel. So if we look into OpenACC, this has its own paradigm of parallelization, own hierarchy. The gang is the largest unit of parallelization. There will be multiple gangs, each gangs are working in parallel. Inside each gang there are workers. Workers are the next group of parallelization, which has all the workers share a same cache. Inside the worker there are many vectors, and vectors are the units of parallelization. OpenACC introduces these 3 levels of parallelization: gang, worker, vector. This helps in these directives to port into different SIMD architectures, starting from multi-cores to GPUs. For GPUs, the mapping is implementation dependent. Some cases a gang is the block. If there are multiple gang, if it is going in multiple GPUs, there are may be multiple gangs. So the gang is the block. If there are if there are going to multiple streaming multiprocessors, each streaming multiprocessor gets a gang, and worker is the warp inside the gang which is operated at once, and there can be multiple warps inside the gang. Like multiple warps inside the block, there can be multiple workers inside the gang, and vectors are the threads of the warp. In some cases we do not need to think about the warp, we just look into gang and then the vector. So this is based on the implementation. OpenACC does this parallelization, that how it will assign workers or whether it will assign worker or not. Compiler, what will be the block size, what will be the thread size. If you do not specify anything, you can do something on specifying the gang on and loop which has to be taken, where the gang will be activated, where the vectors will be activated, where the workers, what is the unit of the workers. You can do something on the specification in OpenACC. You can look into OpenACC best practice guide and find that, but if you do not want to do that, OpenACC will itself do it. If you do not specify any block size, by default block size is 1, grid size is 1, and total number of threads are block size. If you do not specify any block size, it will go to only one thread. But if you do not specify anything on gangs, loops, vectors, OpenACC will do the optimization and run it as the number of gangs and vectors it thinks efficient and optimized for that application. So OpenACC development cycle is typically specified by OpenACC best practice guide and engineers working on OpenACC. So this is a formal way of approaching a large program and see how we can parallelize it. First, you have to analyze the code and determine the places where parallelization is required. How to do that? That you take the code and profile it, find out the total runtime of universal routines with NVIDIA Insight. You can profile it, and there are many profiling software available, and hardware counters. Identify the portions of the code which took longer time and find out which is the hotspot which has to be parallelized. So analyze the code, profile it, and identify which has to be parallelized. Then parallelize that part. See that there are in a code there are particular total runtime is 39 seconds, something takes 30 seconds, something takes 90 seconds, like that, and consider that 30-second part, parallelize it using the OpenACC part, and then look into the, while parallelizing it, look into the data transfer part, look into the non-data dependent locations and use the right parallelization directives there. Once parallelized, optimize that using the loop and data management, and then you get the parallel program. And this is the typical, this is the most formal way of approaching a scientific computing job, that you have your own legacy code, profile it, find out the hotspot, parallelize it, and then try to optimize the performance. We can see an example that this is the immerse boundary based CFD solver, and this was published in one of my students' paper. So we found that 73% time is taken by one particular subroutine, and that has been parallelized, and then it took 43% time, and most of the time is spent on GPU. It went to GPU, and as GPUs are faster, the overall time requirement reduced. And we considered with iterative solvers, and we can see that this basically require iterative solvers. So from multi-core CPU, 64 processor Xeon CPUs, to GPUs, there are 3 to 4 times speed up, 3 to 3.5 times speed up. So it's much GPU in OpenACC tuned GPU can give you, GPU program can give you much faster performance than 64 core processor CPUs. And these are comparison between CPU and GPU time for this immerse boundary solver. In CPU, in a single CPU, it was taking something like 1300 seconds. It came down to little less than 100 seconds in a multi-core 64 processor CPU, whereas in GPU we can see that this time required is around 10 seconds, 10 or 20 seconds. So the performance can be very well improved if you identify the hotspots and then parallelize and optimize a legacy science engineering code using OpenACC. Well, so we looked into OpenACC tutorial from Mr. Sharma of NVIDIA, OpenACC programming guide, best practice and programming guide, and OpenACC.org has sufficient material available on OpenACC which you can start reading and utilize for getting your application ported in GPUs as well as on multi-core CPUs. Looked into OpenACC programming model, data and parallel directives are looked into, and we looked into performance study for a sample case. Okay, thank you.